don't have to. All right, so let's look at hashing. Let's look at hashing more into details, right? So we were talking about load factor already, right? So the load factor measures how full a hash table is, and if the load factor is exceeded, so it's going to increase the hash table size and reload the entires into new larger hash table, right? This is called rehashing, and we use lambda to represent that. So it's pretty much just between numbers 0 to 1, like 0% to 100% full, right, on the hash table. And say the study showed that you should maintain load factor under 50% for the open addressing scheme and under 90% for the separate chaining scheme. We talk about, right, chaining, like this is a chaining, right? Like in each, like when you hash number 2, we found that location, so everything that mapping to that key just go like chaining in there, right? So in Java, hash map used like 75%, right? Now implementing a map using hashing. So you probably understand what's hashing. So it depends on a good hash function, right? To get to the location based on the key, right? And we can measure the performance of the hashing using the load factor. And load factor is the one who increase the table size, right? And maintain the performance by rehash. Now we're gonna talk about a map now, right? So we have the technique to hash. So let's look at the interface for, we call my map. So we have key and the values. All right, so we have clear, removes all the entire entries from this map. Contains key, provide a key, and returns if it's matching it, true or false. We can also do by values. Entry set returns a set consisting of the entries. So it could return like a set, right? If more than one exists. Get, provide a key, get a value back. Is the table, the map, right, is empty. Key set. So pretty much just we can set the key, right? Returns a set consisting of the key in this map. Key set. Okay, actually it's return all the keys in the set. Okay, and we can do put, like add more key and values into the map. So this pretty much all the operation, remove size and values, right, of the map. Okay, now we have my hash map implements this interface, and we have constructors with the load factor and the capacity of the size, right? So this is the entry. So the entry pretty much just that's going to be in the map. So requires to have key and the values. All right. So we have getters, get key, and the get values for the entry. And you see that these are the generics with 2 parameters, right? K stands for key and V stands for value. So let's look at the code. So this is pretty much all the interfaces that we look at, right? Now let's look at this section talk about ArrayList. Store a new entry at the end of the list, and search time will occur in ON, right? If you implement hash map using a binary tree, it's going to be log n, correct? If the tree is well balanced. You can implement my hash map using hashing in order to get bigger of 1 time search algorithms. So let's see how we do that. So it looks like the interface also have an inner class called entry in this interface, right? Inner class is pretty much a class inside a class, or a class inside the interface, my map. Okay. And we have 2 string.
So how does inheritance work with inner classes and outer classes?
Probably when you have an inner class, you pretty much just use this. It's just like you try to use that, but this is implements the interface, right? And then inheritance has to extend from this one. Like this class is like a node, right? So like entry. So if you plan to do inheritance, then you don't want to do inner class. You just do it class outside of the interface. Alright, so now look at my hash map. So let's look at this as a constructor. We just refer to its own constructor right here, right? With the initial capacity and default max load factor. So we're checking just compared to the maximum capacity, since this is an array. We use linked list to implement it. The list of the entries. Right, that's the map, right? Pretty much is the hash map, then we should use array to look at index, right? We already see a structure. So if the initial capacity greater than the minimum or the maximum capacity, then this dot capacity equals to the max, because you cannot do more than max, right? Else, so it does something to trim to power of 2. That's the method, right? And pass the initial capacity. So it seems like, let's look at the method trim to power of 2. Remove here, right? Return a power of 2 for initial capacity. It's just double the size, right? That's what it is, right? So while capacity less than initial capacity, then you can remember we learn about bit, right? Bit operators. So shifting is like multiplied by 2, right? Shifting to the left 1 bit. So it's equivalent to this, but doing this is more efficient, right? Okay. Now come back. This is put. So this is just set the load factor, right? And then create a new table, linked list, using linked list with the capacity, right? Clear How do we clear? Remove all the entries from the map and set the size to 0. Now let's look at how we remove. Here you go. So that is a removes entries right here, right? That the other one removes by key. So this is just to clear. Just loop through the size, and if it's not null, then we just call dot clear. Now let's see, dot clear technically it should put the null into it, right? And this is a because this is linked list, it's already taken care of with that method, right? Linked list pretty much just, it depends on how linked list clear. We were talking about that, right? In the previous one. Like when you implement linked list, right? How to clear. Like you can actually set the head to null too, right?
Yeah, to get a good beagle.
Alright, so now we see the clear contains key. That's the next one, right? So we pass the key. This is called get the key. If it's not equals to null, returns true. That means contains, right? Contains values, same passive values. You iterate to the table. If the table at that index not equals to null. Alright, so this one said we create, yeah, pretty much when we put an entry. So this is a type as entry, right? So linked list, meaning that we can have more than one, right? More than one. So because we know that this is a chaining, right? So when we map to the key, it could returns more than one. So that's why we just want to make sure we just keep looping and put the type entry as a linked list type, because it could be more than one linked list. Table contains linked list, right? Because it is chaining. So now after that, we just loop through the linked list for each of them to search for the values. If it does match, returns true. Okay, else just false. Set. So it's going to return the set of entries. So we create a set, which is a hash set, and then pretty much just loop through it. As long as it's not equals to null, we keep taking that elements for each of those and put into, because it's a linked list again, so put a linked list and we call bucket, because we use the bucket here. And for then we just iterate to the bucket again and put each entry right into a set by adding them. So now we can return the set. So pretty much get all the entries in the map. Alright, get returns the matches, right? So same, this is hashing. So first we have to put in the hash function, otherwise it's going to take too long, right? So by implementing this, it's going to return, like we said, big of 1, right? about. So it's going to get an index. Now we just look at that table at the specified index. It's not equals to null. If it's not equals to null, that means we found right element. So we just put into the, again, this is the bucket, so put into a bucket, which is the linked list, and then we loop into the bucket to see if we find the values. If we find the values, then entry.getValue returns. Otherwise returns no. That means it's not in the bucket or in the hash map. It's empty, so pretty much just if the size equal to 0, the map is empty. Key set. So it's going to return a set consisting of the keys. So we technically just create a new set which is typed as hash set, and then iterate to the capacity or to the map. So same thing, get the bucket back from each table. Now each bucket we just want to add the key, get a key for each element in the bucket, and return the set. Put, now put has to use the hash function again, right? So we pass in the key and the values, right? And we see if we try to get a key, that should return the value, right? Not equals to null. That means we already have the key in the map, right? Then we start to do the key, right? Put the key into hash. Right before we put, we have to get a hash location of the index, right? So we start to put in the map, and now we get the index from the hash function. Now we just need to use that index, right? Put in the bucket, and then we go into the bucket, and then we just get, if the key equals to the key, then we just put the get the values and replace with the old values. And return the old value for the key. Again, right, when we put, we add an entry into the map, right? So we pass the key where we want to put the values, right? So as long as the key is not equal to null, then we technically going to iterate to, we put the key first and we get the index, right? Because key hash for the index, and then we pretty much get location where we want to put the values, right? So we just iterate to that bucket, right? And then we just put pretty much, like in this case, we just take the value and put into that location, and then we set entry with that value. Pretty much if there's an old value, we just replace it with a new value. And then return the old value. Check load factor. So we have to always check that it's not going to exceed the threshold, right? If it does, then we have to, like in this case, just throw exception, like setting maximum capacity. Okay, so this is just create a new linked list if the table at that location is null at that bucket, and add a new entry into the bucket because we found location to add. Increase the size, retain the value. Alright, so remove. So based on the key you pass in, we get a hash code again, we get index where you want to remove. So the same thing, put that index into the map, which is we call table. If it's not equal to null, then we just get that bucket and we search into right throughout that bucket into each key values in the bucket. So this is for each element entry in the bucket. Now if we found, then we just call remove. So it's going to remove out and then decrease the size and break out the program. Then we no longer have to keep looping to find it. So size just return the number of entries in the map. Alright, so values. Return the set, right? A set consisting of the values. So we create a set and we just iterate to the map. As long as if not equals to null, we get a bucket and put into the set. So as long as we can iterate through all of them, then we get everything in the set and return it back. So that's how we get all the values. And this is the hash function. So this is pretty much just based on the what we have learned, right? So this is called checking on two things, right? So pass the hash code and then call supplemental hash, pretty much just has the hashing function here, and make sure that the size, right, not over than the size. So we look at this already. Remove entry, just go into the map and clear it, right? Once we found. Rehash. So this is when it's need like over than the load factor, we just create a new set and double size the set to make it bigger, right? Create a new, use linked list, reset the size to 0, and then just copy, right? So loop, right? Put all the elements right into the new set. Into a new table. Alright, so this is a string, just iterate. So this is just using string builder. String builder pretty much just like a string class, but the difference is this can be changed. String class just return the new version of string. So now it's going to iterate to the map and then append each entry and then print out. So now we have to do a nested loop because it's going to be, so first it's going to be checking less than the capacity, right, of the map, and then if it's still not null and the size greater than 0, then we go to each entry, right, and keep appending the entry. So this entry pretty much is going to call to string of what linked list to print out the list, and then this is just go through the map, the loop, first loop. In this loop, okay. So that's pretty much it, right? How to implement. So now let's look at big O, right? So since we know how to implement,
Can we do like a map class with an array list rather than a linked list, or is it better to do because there's an array?
you can do ArrayList. It's just like array as the bucket. But remember, array, the limitation of array is you have to, like, when is the time that you use array? When you know the size of the bucket. In this case, you don't know the size of the bucket because it could keep increasing, so it's better to use linked list. Because if you make array list, it's just cost when it's a large, right? So clear, big O of what? The capacity, because you're gonna have to clear this array of the map, right? Each map.
So we can just say n is the capacity or
Yeah, the n. So contains key map right way, right? Because hash function, right? We return if you have valid key or not, right? If it's no or not, right? So that's why it's 1. Contains value. You probably have to, depending on the capacity.
content doesn't change. Check to see if there is any value on that hash. Does it?
Contains key.
Yeah. It is just only check the what they call the
Just check the key
check the key.
if it's valid. Entry set. So just return the set, right? So it's going to be O capacity. Get key. Key should be easy because of the hash, right? So it's 1. Is empty, just look at the size. So if size 0 is 1, so key set, get the set of all the keys, so it's had to iterate to it. So it's capacity, right? Put, just do hash function again, map the key and put into the location. So it's about 1, correct? Same as remove, hash function, get a key and remove about 1. Size just return the size, and we keep tracking on the size. Every time we put, we do plus plus, and remove, we do minus minus, so it's 1. Values returns all the values, so it's about the capacity. Same as rehash, right? Create a bigger hash, so it's going to take about n capacity too, and copy the old one to a new one. All right. So the rehashing does not happen very often. The time complexity for the put method is big O1, yeah, because it's not often, yeah. So put will just go into the hash and get the location indexed right away. So that's why it's big O1. So the complexity of clear, entry set, key set, and values and rehash method depend on the capacity. So to avoid poor performance for this method, you should choose initial capacity carefully. So this is just testing the program. So we just look at implementing map, right, using hashing. So this is just implementing set. So we have the iterator in the interface and implements my set, implements it. So we have clear, contains, add, remove, and is empty in size. And constructor, right, my hash set has a constructor. My hash set just implements the interface my set. So technically for the constructor, pretty much is very similar here. maximum capacity, we just do 2 to the power 30, but we just use the bitwise operator. Okay, so this is the load factor, size, create an array, same, right? Create array, use array. This is the same as before. Clear, same, just call it remove elements. Contains, just iterate to it. So same technique, right? Get hashing function, get an index. Okay. And just iterate to each value in the bucket because it's returned right away, right? With the hashing function. If it's equals, then it's true. Add. So if it already contains, so we're gonna say it's duplicate. Subset always unique, not allow duplicate. That's why that's the different than the map. So it returns false. You cannot add. Otherwise, we just going to check for the maximum capacity. So if it does exist, then we have to do the new rehash table to make it bigger. And this is just when we add the elements, we just put the hash code and do the hash function. We get a bucket or the index, right, where to put it, and then we just go to that location. Once it's not known, then we can just add the new linked list to it, like new bucket to it. Alright, so we start to add the index to the new hash table. Increase the size. Remove, so same thing. Put in hash function, get an index. If that location is not null, then get a bucket. Loop into the elements to get that in the bucket and remove at that location. And decrease the size, returns true. It's empty, we just do size equal to 0. Size, return size. Iterator just implements the iterator, which has this one. Just create a new my hash set iterators. So has use the list. So iterator must implement hash next. Right, this is constructor, just set, right, set and list, set to list. So if current less than list the size, so it's going to be true because it still has next. Next, pretty much just go to the next one from the current location and returns the current. Remove, just pass in the elements and we will remove. This is his hash function. Same, we use these algorithms for the hash. So technically the trim power of 2 is the same like before. Remove the elements. So just this is remove all the elements. So that's why it has to iterate to it and create each of them. Clear pretty much how linked list implemented. Set to height, right? And this is called rehash, the same algorithms like what we've seen before. Just increasing the size, create a new bigger table. So this is just turned copy all elements and set to array list. So create array list, loop through the sub capacity, and if each one of them is not null, then we just start to add the elements. Loop through that to string, show everything in the list, in the set. And efficiency creates by the capacity. Contains is about 1, right? Once you found, this is 1 because we use hash function, as well as add, remove is empty size. So you can see now we change from log into 1 now, right? Iterator rehash has to be size of the capacity itself. And this is just testing the set. So that's pretty much end of chapter hashing. Any question on hashing? We just look at how to implement them. Hashing, hash map, and hash set. Alright, so now we can introduce you to chapter 28 about graphs and applications. So can you tell me the real world problems using graphs?
Math. The real world problem is that people try and graph everything, and numbers don't always make sense.
Graphs everything, meaning?
So people take a lot of, this is especially true in businesses. They will take all of their assets, they will take their information they have, they will take customer bases, they take all of the items they sell and such, sale percentages, what goes up, what goes down. They put all this into graphs and they try to make sense of the graphs without actually thinking about the problem.
I see. And what's the benefit of the graph? So
I mean, the graph is a visual. That's all it is.
But this is graph in the term of this structure. So if you look at a map, we can actually apply to the airline, right? So we can use graph to find the most efficiency route. If you want to fly out from a city to another city, like between cities. So that can use graph. Like you can see each dot pretty much a node of each city. And each city has the flying route, right? Like if I want to fly from Seattle to Washington, then probably we go to Chicago and New York, maybe. It depends on time and price of the ticket, right?
Yeah, it could be cheaper to go from here to Miami to Houston to Los Angeles to Seattle.
It could, right? If you go to like those red eye flight, right? Red eye flight that they have it cheap and they want to fill up people.
But if you make a
it may take you longer.
Out, you know, the cheapest tickets prices, you get sued.
Really?
Yes, that happened. Someone went to all the different ticket agencies, all different airlines. They looked through all the pricings and they made a bot that would, if you, someone inputted where they are. So if I input Reagan National Airport and I wanted to go anywhere in the world, I just put where I wanted to go, and they would go through all the different possibilities of all the different layovers and sleep hours, etc., and find you the cheapest way to get from point A to point B. Some guy came up with that as a website, and he got sued for a few $1 million. He won the lawsuit, but he still got sued for it. They didn't like him doing that at all.
I say, how are you gonna get sued and leave or something like that?
No, because the airlines wasn't losing money.
Because the airline was losing a lot of money doing that.
Who cares if they're losing money?
They do.
Yeah,
they're
they
the
care,
one.
but at the same time, it shouldn't be illegal. That's what capitalism is.
Yeah.
That's what the free market is, but we don't have that.
So let's look at, you guys heard about the theory of 7 bridges of Königsberg.
I feel like I'm about to.
I think that talking about that thing over there.
Yeah, the one who found the graph theory. It was found in 1736. Can you believe that? How many years ago? About almost 300 years ago. Huh?
One take a walk, cross each bridge exactly once. Cross each bridge exactly once, and then return to the starting point.
That guy is too smart.
Mm-hmm. He's thinking about their 7 bridges, 2 islands, right, on the river. The city, the 2 cities, right? City and island were connected by 7 bridges. Look at this image. The question is, can one take a walk across each bridge exactly once and return to the starting point?
Yes.
How?
Alright. From the bottom left, cross into from the bottom left from B.
Okay.
Cross, go up.
Where? Which one?
And
Island?
from the far left. Go
Here.
up.
Up.
Go up again.
Up to where?
Up
Tell
to
me.
the left.
Here.
Go to A, the bridge at A. And go down twice.
Again here?
Yeah.
Okay.
Go over.
No, it doesn't work.
No,
Yeah, it doesn't work.
keep waiting.
No, it doesn't
Go to the
work.
right.
Okay.
Go up. Go to the left. Swim back to A. They never said I couldn't.
No.
No, the
Doesn't
question
work.
parameters is, can you walk over each bridge? Can you bridge once?
What's the point of walking over bridges if you're gonna get wet anyway?
Maybe I wanted to go for a swim.
Yeah, sure.
You know how hot Virginia can get.
So,
I don't
someone
think
come
this
up with
was
the algorithm.
Virginia.
for the
Not the
zeros?
algorithm, just a graphical solution. Because there's
Oh.
3 bridges all lead to 1 point.
I mean, technically, it's
So it looks like you cannot do it.
I mean, computer science uses the word algorithm whenever we don't want to explain anything. Oh, how'd you do that? Oh, I used an algorithm.
And
So where do you have to start? Do you have to start at A?
I mean, you can start anywhere, but it's not possible because.
but the question is, how do we prove, right, that if it's possible or not? Because there's so many possibilities going on, right? People can keep thinking and thinking, right, at that time and see, just like him, it may be possible. But he said it is impossible to do that by proving with a graph. To show all the possibilities using graph, right, to prove. So Euler, like to establish the proof, Euler is the one who found that problem. So he said he created that using a graph model, right, eliminating all streets, right. So sketch the new one right there. And city, island, those are the nodes, right? And the connections, the bridges are the, we call arcs. Vertex, right? Sometimes the dot or nodes we call vertex. And bridge, which is a line we call edge. Okay, we call edge. And this whole thing we call graph. So by looking at the graph, ask whether there is a path starting from any vertex. So look at vertex. Is there a path starting from any vertex? Traversing all edges exactly once.
Can you cross the islands? Can you go from like A to C? And C to B?
There's no path, right?
Oh, okay.
I mean, A to C, yes, right there, right? But you say A to B, there's no path, right? And returning to the starting vertex, right? There's no such that path, right? So for such a path to exist, each vertex must have an even number of edges. So that's why there's no solution to this.
Oh, so there's no solution to either?
Because you always have one
Mhm.
that's left over.
Yeah.
Hence, swim to shore and cross the last bridge.
Is a boat.
So now graph. So it's being used in computer science, in math, in biology, engineering, economics, genetics, social science. So we use algorithms. We call depth first search and breadth first search. So it's based on these algorithms. And you learn these algorithms. So we're going to find a minimum spanning tree, the shortest path to the destination. And we're going to look at wedges graph. So looking at the map before, we can see that we can create vertices of the cities using this. This is just show a set of vertices, and this is a set of edges from Seattle to San Francisco, from Seattle to Chicago. So this is just another way to write a graph in a mathematical models.
It's just showing the line where it's going.
Right, just from here to here
starting to end
with the
of that
set.
line.
So now we also have a directed graph, like a one-way, right? Like directed with the directions. And we also have a complete graph. Complete graph, pretty much each vertex, they're connected with one edge. Like all of them are fully connected. If I want to travel to B, C, D, E from A, I can just take that path, only one edge, and we'll get to there. So this is called fully or complete, right, graph. And we have a subgraph like that. This is just a partial graph, right? And these are undirected graph because there's no arrow, right, pointing. If there's an arrow directed, then you cannot go back, right? You can only do one way. Now, when you look at these are edges, right? The connecting thing between vertex. We can put the wedges on it. Like now we see this is unwedged graph. So wedges could be like the distance between each vertex, or the cost, and so on. So those are the wedge. Now, two vertices in a graph, this can be adjacent. Adjacents mean they can be connected with the same edge that we can travel. Like B is not adjacent to E, but adjacent to A, right? Because they're connected. But B and E, they're not connected in this case. So they're not adjacent. And the degree of a vertex is the number of edges So what's the degree of B?
A, C, E, D, all of them.
Mm-hmm.
Because it's
Two vertices are called neighbors if they are adjacent. Two edges are called neighbors if they are adjacent. Now we have a loop, right? A loop is an edge that links a vertex to itself. Like it can have the path that put back to itself, right? This is called a loop. So simple graph, we have the parallel edges, right? Let's see. If two vertices are connected by two or more edges, then this is called a parallel edges. Simple graph is one that doesn't have any loops or parallel edges. A complete graph, every two pairs of vertices are connected. Seen it. So a graph is connected if there exists a path between any two vertices in a graph. So we assume that a graph is connected and undirected. A cycle is a closed path that starts from a vertex and ends at the same vertex. A connected graph is, if you look at it, is pretty much a tree if it doesn't have cycles. Like a tree can be a graph. So this is just show an example of the graph here. So now let's look at in virtual. Okay.
What was the graph we used, or the graphing tool we used in 200? Was it Raptor, I think?
Say again.
I said we used a graphing tool in CSC 200. I believe it was Raptor.
Oh. Yeah, I introduced Raptor for the flowchart.
Yep.
So let's look at DFS is the depth first search. BFS is a breadth first search. Like, remember we tried to search, right, for a vertex, right? Now, all of this is all about what? Efficiency, right? So you're going to have the starting vertex, right? I started at the vertex, right? I could add the edge, right? To connect two vertex, right? Two vertices. All right, just create a graph. Okay. So starting vertex 0. Oh, this is going to show depth first search and breadth first search. So let's let's look at this one first. So what's depth first search? Depth. So it's pretty much just, if you look at, we have a graph. I'm starting at 0. I want to travel to okay, 5. How many ways I can do that? There are many ways, right? But how do I list all the possible ways? So we can use algorithms called depth first search. So depth first search pretty much is showing you, it's going to go by the depth, okay? Since these are the rate one, right? It's only worry about, you can go from zero. It's just want to visit all the vertex, all the vertices. Okay. I just want to visit all the vertices in a manner of go by the depth. Like from 0, first thing should go to 1. Okay. And from 1, I should go again like in the depth right path. If it breadth, that means it's spanning from it on, right? If you look at one more time, 0 to 1, 1 to 2, okay, that's it. I cannot go further on that side, so I have to go to the other side. 1 to 5, since I visited, then I visit the next neighbor. Just look at the adjacent. 3, and 3, the next neighbor is 4. Done. You just go into the depth, like deeper, right? But if you look at breadth, it's expanding. It didn't go into a depth level. It's breadth, right? So from 0, I visit 1. I come back, I visit 2. Come back, I visit 3. Come back, I visit 4. So it's just like I have to visit all my neighbors first, right? And then I have one more to visit, which is 5. Then I can just go down from 1 to 5. And that's it. The way that they're visiting all the edges. Okay, just
So
in the
you
depth
choose,
or in the
you
breadth.
choose 1 to 5 because the 0 and 1 is the closest. When it goes to 1, then it's fine. 5 is the closest, right? That's why.
Like this one is, there's no closer because there's no wedge. There's no wedge. So we just go probably by the order of the numbers. After 1, you want to go to the depth 5. Okay. So we understand depth first search and breadth first search, right? Just the way that they visit all the edges. Now, once we have all the possible ways, right? We pretty much just look at the charted path now. Like, if I want to go from 0 to 5, right? Which way is the charted path?
3 to 5.
0 to 3 to 5.
It says 0, 1 to 5.
I go on
Like I said, this one they don't look at, there's no wedges. If there's wedges, I'm going to have to write a distance, right?
that. Yeah, can I get numbers on those lines, please?
But they just look at the orders for this one of the 0, 1, and 5. Okay.
So if it's instead of 1, if it's like 4, so it should have gone to 0 to 3, then 5.
If I what?
If instead of 1 up there, if it's 4, then it would go to 0, 3, then 5. Right. just change the place 1 and 4.
Switching them?
Yeah.
How?
No, but I'm saying if we do that, then it's gonna take the 0 to 3, then 5, right?
Oh, it's still 0, 1, and 5. It's gonna go 0,
It takes,
1.
if you switch 1 and 4, it's still going to take 4. I mean,
It's always going to take the same path. So it's trying to find the shortest path. It doesn't matter about what number it is.
I was just complaining because there's no numbers on the lines. I don't know how long everything is away
Yeah,
from each
no, I
other.
was going to say,
Because
looks
I feel
like,
like
0,
that-
0, 1 to 5 looks longer than 0, 3 to 5. That's why.
Yeah, because I feel like the triangle is smaller than what they call 0, 1, 5. So
So
that
3 to
means
5 looks like it's the shortest path visually.
It said 0, 1 to 5 is actually the shortest.
I didn't have to shoot that actually.
So how about 0 to 6?
You know, it's probably gonna be like 0, 2, 5, 6.
It should be just 0 to 6 because that's the right path,
What
right?
about 4?
yeah, just direct 4.
Let's do 2 to 6.
It's gonna go to 0, 2, 0, 6.
We got it, right?
Yeah, because only 2.
Mm-hmm.
What about 1 to 6?
Oh, do 2 to 5.
Which one am I gonna do first? Okay, let's do
2 to
1.
5.
He said 1 to 6, right?
1 to 6.
Where's it gonna go?
1, 0, 6.
1, 0, 6.
Yeah, it's the shortest, right?
Do 2 to 5.
It's gonna go 2, 1, 5.
Yeah, 2, 1, 5, right? That's gonna be the shortest, right?
So does it try to take the route with the least amount of vertexes? I think that's what they're called.
Mm-hmm.
Okay.
Is it just doing vertexes or is it doing distance?
I think it's doing vertexes.
Because we don't have the wedges graph yet. If wedges, then we look at the distance.
Yeah, can you move the vertexes? Like, can you move 6 down? Yeah, like move 6 down.
So you can to where?
Just down, like, adjacent to 4.
What do you want to do next?
Test 2 to 6 again.
It's gonna be 206,
Yeah,
right?
it's 206 because it's vertex, right? Not distance. The point was to make 6 closer to 2's bottom side, so that distance-wise it'd be closer. But the it'd be a short amount of vertex
Alright.
to go through.
3 to 6 looks closer, I think, right? But it should take 0 to 6, if I'm not mistaken.
Oh, I can just remove it now. So all right, so you were talking about if I want to do before I see. I think that's it, right? We understand, right? Okay. So we just write an array of vertices, right? That's how you implement.
Vertici. Wait, would the plural of vertices be vertici?
I think so. Actually, isn't vertices already plural?
Vertices? Vertices?
Vertex is singular.
Vertex, vertices, vertici.
No, because vertices would be plural. And
Okay.
vertex would be singular.
English is weird, man. Not my major.
Word matrix. Matrice, right? Matrices. Matrices.
See, like English has all these rules about how it's supposed to work, and then it just breaks the rules whenever it wants to.
It's because when it's trying to import the
Vertices.
meaning from other languages, and other language doesn't work like the base English languages, then it just
Vertices.
adopt to that
When
language.
people decide, when English decides it wants to take, something with Greek or Latin roots and then make the French spelling of it, something like that.
All right. So we create a class city to represent the city, just like now your project, right? So this is we're moving to A4, right? Project. So now we're doing like person. We already have that class, right?
Yeah.
So this is just showing the city, right? Set population, set major getters and things like that. So create an array, right, of the object of vertices. Now let's look at how we're going to create the age. So you could create a two-dimensional arrays, and you can make a link, pretty much a set of these are the edges between vertex 0 to vertex 1, vertex 0 to vertex 3, just like the connecting, right? We start to connect them, like vertex 0 pretty much is connected to 3 other vertices, right? Vertices like 1, 3, and 5, right? And start from vertex 1 and their neighbors. Make sense? So that would work as for the other vertices. So now look at just showing again the same thing here, right? Ages and vertices. We create a class called age.
What does the U and V stand for?
This is 2 point when you connect that to line.
Yeah, this is just the
Do they
like
use
coordinates,
U
right?
and V for a reason? Kind of like how they did key and value?
This is just showing you another way, right?
Okay.
The first way we can do two-dimensional arrays. But then I said, okay, there's another way.
So,
You just create a class called age to represent the age.
so in
And this is just the from and to,
Okay.
like you like from and to.
Mhm.
You can set from and to, right?
So in actual map, we can just use the longitude and the latitude as our value U and V, and then find the closest like a route. No? Because then I was thinking the longitude and that thing.
Remember, what we try to do, we create person class. After the person is created, those are the vertices, right? And we don't give the ages yet. So like this create account, right? So people keep creating account, right? Now we have a lot of network of people, we start to create the edges based on the criteria. We ask, once this guy create account, we ask the question, what do you like? What food do you like? Remember we said food, right? This guy said, so that's going to be the edges. This guy said, I like Chinese food. This guy, I like Chinese food. They get connected. So we gotta create the edges based on the criteria, right? So if this guy also like Chinese food, right? Now we can have a group like on the left. We already have a graph of people who love French, right? And we may have like these two guys pretty much get connected because they also like Chinese food, right? So we start to have a group, but this guy doesn't like Chinese food at all. So this guy happened to like pizza. But this guy also like pizza. That can be connected, right? Like that. Make sense? So at the end of the day, you see that all people in the world, they're gonna get connected like Facebook, I guess. But I'm not the one who make Facebook, but what we gonna do? We just, at the end of the day, they're all gonna get connected. Even like 24 and 5, they're not connected because they don't like Chinese food. 24 and 11, they're not. But it happened to be 17 also like both. When we first start, we have the check boxes.
I don't even know when I created it. I don't know when I clicked on it.
So that's pretty much your A4, right? You start to construct a graph. And then we're going to start to implement depth first search, and find shortest path. Like, I'm going to locate, like this guy could live in Seattle. This guy could live in Virginia, right? And we're going to find the shortest path between these two guys, something like that, right? So how can we, let's say for example, we get another, this guy loved Korean food, this group, but none of this really like Korean food, right? How we gonna get 0 to get to 14?
Music, there's something else connected.
Maybe music.
So that's why we start to, in Facebook, they start to suggest, right? You suggest, recommend friends. Remember, once this 11 who love pizza get connected to 17 as a friend, then they suggest 24, 8, and so on as a friend to 11. Because this could be people from your high school, right? Woodson.
Geolocation as well.
This could be the Woodbridge High School, right? And now this could be Annandale High School. Then now it happened to meet at Nova. They add friends 17 to 11. Or then you might want to
18,
connect to
15
24.
together.
Now, when you said added, remember when you said okay added, then you create an age. Right there. Once you add a friend, you create an age. And this whole thing is what? Marketing, right? Like, hey, we have the new iPhone X. 11 said, I recommend it. So start to recommend to all the friends in the network.
It's creepy as once you get enough people in the
But
network, so
but the whole thing is all about, I want to think about, I want to make a connection, the network of people as much as possible.
So
And with this, you can see this theory going to make it so fast.
you can continue with that. So 14, 21, 20, 6, and 14 are connected to another diamond around 22, but not connected to 22. Let's say 22 doesn't have a Facebook or whatever the marketing thing is. If those 4 people talk enough about, and they talk about 22 because all 5 of them are friends in real life. You can start to make the connection into 22 as if they had an actual connection, even though they don't have a real connection. And that's what Facebook's been doing for a while.
Yeah, like the challenge now, you see that we never get a Korean group to connect to this Chinese and
Look at
French.
20's not connected.
So that's a challenge. And if I want to promote the products to Korean, I never get into Korean market at all. Okay, so that's your project. Make sense? You already learned the theory now, right? How to create, how to add, right? Okay?
Are you using our projects as like some type of marketing scheme?
Yeah, he is.
No, this
wanna
is
learn
just
my
apply to the
scheme?
application.
It's like, oh, you have the best scheme here, so I'm going to use yours. I'll cut you in
5?
Only 50.
Now just think about how to do it.
Walk.
Just think about, but you have an idea how to create graph, how to make edges based on the recommendations and based on the ad frames, right? So those are the criteria. So that's what we want to do. Like I said, I don't know. This is just, I thought it's going to be this way. What do you think?
Yeah.
You never think about this, right? Yeah, I never think about it, but I think I just look at it. I thought,
I think on paper, marketing's cool. Like, oh, this is a cool idea. This is a cool idea.
and what we going
in the
to,
real world,
yeah,
it's scary.
we're going to see this one. You just make that up, and then we can just test with maybe recommend professor,
It's all marketing.
right?
It's not really lying. It's more like abusing psychology.
Because you guys being registered for classes, then let's see. This is Professor K. This is Professor Daniel. This is.
I'd love to register for your class next semester, but I'm not going to be here.
All right.
You're teaching 205?
Yes.
I heard 205 doesn't get transferred to Mason. Is that true?
Yeah. It's just for
transfers
SSA.
elective.
Yeah, it's
I think that's pretty much what you want to stop